Morning all. Welcome to day 2 of Melody Has a Migraine. Fun fact about my migraines, my migraines affect my vertigo, and so I end up not being able to drive. So I can't get from my house to MTSU, so I'm going to try something a little bit different today. I do have to cancel classes again today, which I really don't like doing, but I don't feel like I have a choice. So we're going to, instead of asking you to spend an hour in class yesterday and an hour class today, I'm going to ask you to spend about 45 minutes online today watching this video, pausing it when you need to take well, that's going to be annoying. Pausing it when you need to take notes, and then at the end, I'm going to direct you to look at the first, 7 or 8 problems of your Module 2 homework and see how well things are sticking. Right now, the plan is that you would have a test on Monday. I feel like that's probably not fair after missing 2 days of classes. So we're going to push that to Tuesday and Wednesday, which means all the classes that normally meet on Tuesday will have their test on Tuesday. And the one class that doesn't meet on Tuesday, which is Section 8, the 11:30 class, they will have their test on Wednesday. So I am hoping to get back to campus tomorrow, Friday, and I will be in my office starting at 8 o'clock tomorrow morning and be in my office until classes start at 10:20. So if you watch this video and you do some work and you find that you're feeling panicked about a test coming up so soon and you want to come and talk to me, please do. I am there for you. So let's go ahead and get started. I am going to work with the Section 8 notes, and the reason for that is because Section 8 did not meet did not meet on Tuesday when we would have had our last class session. So they are the furthest behind at this point. This is what they would have done yesterday. So if you are in sections 6, 11, or 12, you may feel like you need to skip forward a bit until we get to the slides that pertain to the Alan and Alyssa problem. But moving through these first few minutes won't hurt you at all. So feel free to kind of refresh your memory. So in the prep work, what I asked you to do was to consider problem 7 from module 4. I think this is investigation 3, and think about this situation that we have here. Bob's distance in miles to the finish line of a race is y, and x is the amount of time in minutes since Bob passed the final water station. So we were asked, what does the point negative 22, 8.2 represent in this situation? So we're trying to translate from an algebraic statement into a contextual piece of language, and well, that's weird. Why is it not working? There it goes. I have not used this feature on my laptop before, so sorry, there may be some bumps on the road. In general, what I was finding from students is that 22 minutes before Bob reached the last water station, he was 8.2 miles from the finish, which is absolutely true. I had a few folks who wanted to say that he was 22 minutes from the last water station and also 8.2 miles from the last water station. But remember that 8.2 is an output value, a y value, and y in this context represents Bob's distance in miles to the finish line. We were also asked to think about what well, that's sticky. What the, oh, I see. It was just adding random things. Pardon me. I'm just going to keep talking to myself. It's what I do in class anyway. It should make you feel at home. So the second thing we were asked to do was determine the value of m, the constant rate of change of y with respect to x. We talked in our other classes about the fact that some folks wanted to say that this was, here we go, change in y over the change in x. Others wanted to say it was the change in x over the change in y. But that phrase, with respect to, lets us know that the independent variable is the x. And so what we really have here is not going to be the change in x with respect to the change in y, but the change in y with respect to x. And this is how we would notate that right here. So let's take a moment, and you might want to pause if you didn't do this already, and calculate the change in y over the change in x. Further up on the page, it gives you a formula for that. It's just the slope formula. You guys have used it before. So we would take this, this 8.2 and this 2.2 and subtract, and then divide by the difference between negative 22 and 3, which would give us negative 6 over 25. And some folks wrote that as negative 0.24. So there's a couple of different ways to look at that one. And then the other part was, and say what this value represents. That was the part where I got the least input from you guys in the prep work. And it's one of those things that I really feel like you need to understand well. So let's talk about that. Take a moment if you want to, and pause for just a moment and double check. Make sure that you understand what this change in y with respect to x is really saying. When we talk about the slope, we're talking about, we're talking about these different variables. We're talking about Bob's distance in miles to the finish line, and the amount of time since he passed the final water station. So what we have here is distance over time, or even let's put it this way, the change in distance. I'm gonna pull up my change here. The change in distance divided by the change in time. And that is significant. That's something that we need to think about. So in most of there were several folks who were able to say that this change in distance over change in time in this context represents the fact that for every 25 minutes of running, Bob gets 6 miles closer to the finish. And that's true. Absolutely, that's true. In fact, this idea of 6 miles closer to the finish kind of absorbs the negative 6, right? So we know it was negative 6 over 25. So that negative 6 is indicative of him being closer to the finish. So there's less time to the finish, less miles to the finish. Another way of writing that would be that Bob is running at 0.24 miles per minute towards the finish. So that's another way to say that same thing. I'm going to shrink this up a little bit so that it's a little bit easier to see. There we go. So we've got these two different interpretations, but both of them are based on this idea of change in distance over change in time, miles per minute. And when we look at that, that should be familiar. We should be able to recognize that miles per minute is a common way to think about this rate of change. Miles per hour, feet per second, these are normal things. We don't normally drive along the interstate and see that we have so many hours per mile. It's generally stated as miles per hour, right? So that should help us to think about that. One of the questions that I asked in class was trying to figure out how far the water station is, that last water station, how far that last water station is from the finish line. So I asked the question, how far from the finish line is the final water station? Now, if you're really engaged in this, if you're really thinking about this, I'm going to encourage you to pause the video right now and think about, what does that imply? What are we really looking for when we're talking about how far is the final water station from the finish line? I'm putting an extra copy of this this graph. No, I don't need your design ideas. All right, right here, and hopefully they're gonna help us to kind of think about that. We'll take a moment and pause, and once you've done that, we'll keep going. So hopefully you've taken the time to pause. One of the things we talked about on at the end of last week when I assigned this prep work was to consider, where is the final water station and where is the finish line? So if the finish line, if the distance to the finish line is measured in y, right, in this, this y variable, then the finish line, we will have reached the finish line when y is 0. So we will have reached the finish line along the x-axis where y is 0. Likewise, if the amount of time remaining, or the amount of time since Bob passed the final water station is denoted by x, and we noted that negative values imply that we have not yet reached the water station, well then the water station, then the water station is along the y-axis. So if we're looking for how far the finish line is from the water station, then we're looking for the y-intercept. We're looking for where does this graph cross the y-axis. So if we looked at a line through there, and that's not a good one, but if we looked for a line through there, then we would see that where it crosses the y-axis is going to be the finish line. Several folks in Tuesday's classes supposed that it was at 3. And if you draw a nice straight clean line, unlike the one I've just drawn, you do get something that looks very much like 3. But what we want to know is precisely how far from the finish line is the final water station. And that we can't get by eyeballing it on the graph. So we need to do a little bit of math. If we want to find the y-intercept, we can do a couple of things. We can say we know that the change in y with respect to the change in x is going to be negative 0.24. I'm going to use the negative 0.24 both because it's exact and because the notation is a little bit simpler and my stylus is driving me crazy. So we've got this change in x over change in y over change in x, this slope, right? We know that this is the slope. We've denoted slope as m since we were in middle school, so that should be pretty familiar. So from here, we want to be able to say, okay, so could we apply the slope either to this point or to this point and figure out what that slope is? Could we count it back? Could we count it forward? Some folks wanted to use the suggested formula down here. This y2 minus y1 is equal to the slope times x2 minus x1. Totally reasonable, because when you think about it, if we say change in y over change in x, well, what is the change in y? Well, it's the difference between the y values. Same thing for the change in x. And so that should give us m. And if I just multiplied by the denominator here, this x2 minus x1, it becomes this equation right here. So we could totally do that, absolutely. Somebody in one of the other classes suggested that if y equals mx plus b is a way to find, the equation of a line, then y minus mx equals b might be a really helpful way to find that y-intercept. And that is the simplest of the methods. You can use any of the methods I've mentioned. And it should work pretty well. You should get to the same conclusion, but for simplicity's sake, we'll just use this really simple method here. So we said if we use one of these points, and it doesn't matter which one, we're going to use negative 22, 8.2, and the slope, which we know is negative 0.24, then we should be able to say that 8.2 minus negative 0.24 times negative 22 is equal to this b, this y-intercept that we know that we're looking for here. And if we do that and we do all our calculations correctly, we should get 2.92. Okay, so there he is. So the water station, let's write that out. The water station is 2.92 miles from the finish line. So taking a look at this, we've explored some things about the rate of change that have been helpful in figuring this out. If we know that this is true, that this statement right here is real, then we should be able to use that to answer questions like these two. Now, these two are not in your book, so if you're using your workbook, well, here's the deal. So there were some other problems that were supposed to ask these same kinds of questions, but in a different context. And when we got rolling on Tuesday, we were in this context already. We had it in our brains, and I didn't want to break that context and go to a new one. So I just kind of added these questions to this context. So if you are in your workbook and you're thinking, well, that's really annoying, Melody, I don't have room to write that. You're right. I am annoying and you don't. I would very strongly suggest that you grab some Post-it notes and just keep going. So pause and do that if you need to. But here are the two questions that we need to address. We need to address, starting from 22 minutes before the final water station, Bob runs for 6 more minutes. How far does he get? And then likewise, starting 10 miles before the finish, Bob runs 5 more miles. How long does it take for him to run those 5 miles? So when we do this, several people in class went about this different ways, right? So starting from 22 minutes before the final water station, he runs for 6 more minutes. So minutes are our X variable. So we could look at that as this distance in here, right? So from 22, that would be from like 22 to 16, right? So that's about right. So we've got this change in X of 6, right? I'm going to try flipping my, no, I'm not either. Anyway, so we've got this X equals 6. So when we're looking at that, we're trying to figure out what is the corresponding change in Y. So we're looking for what is that corresponding change in Y. My stylus is not being nice. Now we could do that by figuring out using the slope and the y-intercept that we found before. We could figure out what is the output, what is the distance from the finish line when x is equal to negative 22 plus 6 or negative 16. We could totally do that and then find the difference between 8.2 and this new value. Absolutely we could. But we could also lean on the fact that we know that the change in y is equal to the slope times the change in x. So in this case, that means that the change in y is equal to negative 0.24 times the change in x. So what we can do is we can say, hey, look at this. We already have the change in x. The change in x is positive 6, right? We've run for 6 more minutes, so this is going to be a positive 6. We've got negative 0.24 hanging out here. And if we multiply those together, we should get the change in y. In other words, how far does he get is the change in y. They're not asking how far is it to the finish line after 6 more minutes. They're saying how far did he run in those 6 minutes. And so this actually really answers our question nicely. So what we've got is this negative 1.44. That's terrible. This negative 1.44, or if we used words to talk about this, we would say in 6 minutes, oopsie, Bob ran 1.44 miles closer to the finished. My typing skills are terrible this morning. So we've got this, and I'm going to put that in bold so that it doesn't look like it's the same as the question. Anyway, so we've got this conclusion that we can draw from the 1.44 that we found. So this also works if we're looking for the opposite, the change in the the change in the X value. So it says starting 10 miles before the finish, Bob runs 5 more miles. How long does it take? Now this one was kind of a forced question because if you try to solve this one by finding both points and then finding the distance between them, some things become a little sticky. First of all, starting 10 miles before the finish means that we are, that we are way yonder up here, right? So this is 10 miles before the finish. So we would have to figure out what is the corresponding point here, and then we'd have to count forward 5 miles. So we would have to look at this point right here, and we'd have to figure out like where are we here, and we'd have to find that change in Y versus the change in X that way. When if all we're looking for, if we've got the change in Y, I don't think this is going to stay on the thing. Anyway, we've got the change in Y of -5. We're reducing the distance from to the finish line by -5. We're really looking for the corresponding change in X, right? That's all we're really looking for. So we could apply this again. We could say the change in Y is equal to 0.24 in the negative times the change in X. And then if we've got the change in Y as 5, -5, then we've got -5 is equal to -0.24 times the change in X, and we'd have to calculate that. Let's see here. So if we do that, then we've got -5, right? -5 divided by -0.24. I don't know where my, oh, there it is. Hit enter, and it's going to be right around 20.8 minutes to do that. And that's a really logical, conclusion because it took us 25 minutes, took Bob 25 minutes to run 6 miles, which is pretty damn speedy, right? Bob is really hauling it. And so we've got this, the change in X is going to be approximately, is going to be approximately 20.8. So it takes Bob about 20.8 minutes to run those 5 miles closer to the finish, right? So let's put that over here. See if we can get that to fix. Okay. Well, there we go. All right, so we've got the answers to those questions. And that brings us to where we were going to start yesterday in class with the rest of the sections. Sections 6, 11, and 12 were meant to start about here today. In particular, I wanted us to take a look at the Allen and Ellison problem. Notice that I'm skipping like 3 slides in here. Those are the ones that would have addressed these same questions with a different context, and you can ignore those for now. If you're curious, you're welcome to read through those problems and see what you can do with them, but it's not like I'm going to ask you to do them for a grade or anything. So take a moment, take some think time, summarize that last problem, make sure that you're feeling good about it, rewind if you need to, and go back over some things, and then we're going to start the Allen and Alyssa problem. So what I'd asked a couple of the sections to do for class for Wednesday was to diagram the Allen and Alyssa problem. It's very, very similar to the Becky and Wendy problem, and so it shouldn't take too much to make that happen, but here's the deal. Allen and Alyssa are attempting to find each other in a crowded mall. They finally spot each other near the food court, at which point they are 140 feet apart. Right? So we've got 140 feet. Goodness. They begin walking towards each other. So I'm going to put Allen over here and Alyssa over here. It doesn't really matter which one's where. Let's see here. Allen travels at a constant rate of 5 feet per second, and Alyssa travels at a constant rate of 4 feet per second. So as they're traveling towards each other, right, I'm going to change colors here just so that I can denote the difference here. So we've got Alan's distance here. We've got Alyssa's distance, which should be slightly shorter here. And then we've got the distance between them. So Alan is traveling at a constant rate of 5 feet per second. So if I say that, I don't know, T is the number of seconds that Alan has been, in fact, let's write that down. Let's say, let's just be real specific here and say, let T equal the number of seconds since Alan and Alyssa spotted each other in the mall. The last part is probably not all that necessary, but anyway, if we call that T, then we can say that for each passing second, Alan has covered 5t seconds, and 5t feet rather, and Alyssa has covered 4t feet. Okay. Now, what they want you to do with this is to be able to think about what is the space that remains here. And so many of you are probably going to already have an algebraic idea for what we would call this middle distance. But let's just make sure we're all feeling good about it before we get too far into it. This next slide talks about finding those distances. How long will it take for Alan and Alyssa to reach each other, that kind of thing. This is the next piece down. So this was part A of number 5 in module 2 investigation 4. And then the next pieces ask you to think about, after 0 seconds, how far are they apart? How far have they traveled? And the same thing with several of these. So I want you to pause, and I want you to take a moment to answer those questions in your book. They look a little bit different than this. I formatted it for class because that way we can all kind of engage in it together. But I'd like for you to pause, take a moment, and see if you can complete this chart. It shouldn't take too much time or too much effort, but take a minute and do that. So I'm going to go ahead and start filling this chart out. After 0 seconds, Alan has traveled not at all, Alyssa not at all, which means there's still 140 feet between them. After 1 second, Alan's gone 5 and Alyssa's gone 4, reducing the distance between them by 9. And so I've got 31 feet. Well, excuse me, 131 feet. Goodness. After 2 seconds, he's walked twice as far. She's walked twice as far, reducing the distance between them by 18, which is going to leave me at 122. After 4 seconds, I get to double again and double again, reducing the distance between them by 36. At 8 seconds, I get to double again and double again, which reduces the distance between them by 72. After 10 seconds, Alan, so this is not doubling, right? We've got doubling 0, 1, 2, well, 1, 2, 4, 8, that's all doubling. But after 10 seconds, Alan should have traveled 50, Alyssa should have traveled 40, reducing the distance between them by 90, leaving them 50 feet apart. So this is the question. We already know that this is 5n and that this is 4n. In fact, just for consistency's sake, well, whatever. I'll do that in a minute. We've got 5n and 4n, which is going to reduce the distance between them. So we've got 140 minus the 5n and the 4n together. Or, in other words, 140 minus 9n. So we've got this reduction by the distance that they have walked. And so if we go back over here, we could relabel that as 140 minus 9n. Get that 9 in there better. All right. Okay. And they asked this question, how long will it take before Alan and Alyssa reach each other? So the distance between Alan and Alyssa, so if we wanted to add to this, in fact, let's do that this way. Let's say that what we're working from is this 0. if we want the distance between Alan and Alyssa to be 0, well, then when we backtrack, we have to consider what's happening here. What is the n that allows that to happen? Where is it that 140 minus 9n results in 0? And that's a pretty easy equation to solve. So we could subtract from both sides. So we could say that's a negative 9n equal to negative 140. We could divide both sides. We could divide both sides by negative n, or negative 9. Excuse me, I should have turned my notifications off. I apologize for that. And we'd end up with 140 divided by a 9, which is about 15 and 5/9. Okay, so we'd have about 15.6 seconds. And because we're working in time, and we're working in seconds in particular, this idea of approximating becomes important. It's so we've talked about being exact, being as precise as possible. But if we're going to give an answer in context, for example, how long will it take for Alan and Alyssa to reach each other? Approximately 15.6 seconds. Unless you are really good at subdividing seconds, which most of us are not, then stating that as a fraction, which it would be 15 and 5/9, stating it as a fraction is not as useful, right? So this idea of precision comes back to us again, and we have to make sure that we are being precise in a logical way. And so that's really what we would have gotten through. We would have finished up the Bob's race problem, and we would have gotten into the Alan and Alyssa problem yesterday in class. And we would have begun to think about the first problem in Module 2, Investigation 5. So I want you to hit pause, take some time to think about this problem, make sure it's set well in your head, and consider things like, for example, if I wanted to know how long will it take until there's 10 seconds between them, or 10 feet between them? How long will it take until there's 32 feet between them? Those kinds of things. How would I go about that, and how does this equation writing help with that process? So pause and think about that, and then restart, and we'll start on Module 2, Investigation 5. Okay. Now this one's a little bit different. A car is driving away from a crosswalk. The distance d in feet of the car from the crosswalk, t seconds since the car started moving, is given by this formula, d equals t squared plus 3.5. This particular problem is a little different than the others because we haven't had a t squared in any of our formulas just yet. And consider for yourself, what does that imply about the shape of the movement? What does that mean about the way that the graph moves? In particular, you guys should be sparked to say it's not linear, right? A linear function has a single variable at its degree 1 level. So y equals mx plus b. There's an x. There's no exponent. We're not acting on x in any other way other than just multiplication and addition. And it's only acted upon just that one time. So the big difference here is that we have t squared plus 3.5, which means it's not going to be linear. So take a moment, pause, and look at parts A and B and see if you can begin to see what this is going to do. The first question says, as the number of seconds since the car started moving increases from 1 second to 3 seconds, what is the change in the car's distance from the crosswalk? Okay, so that means that if we're going to start playing in this graph over here, and they're going to ask us to do that in part B, then we need to, my son's sheets are done in the dryer, and that's going to buzz again. So anyway, so let's talk about what's happening here. As the number of seconds since the car started moving. Oh goodness, is my recording still on? Yes, it is. Okay, cool. Sorry. Just had a panicked moment there that I was talking to myself and not to you guys. Anyway, as the number of seconds since the car started moving increases from 1 second to 3 seconds, was the change in the car's distance from the crosswalk. So at t equals 1 second, the distance is going to be, okay, well, that's 1 squared plus 3.5. So that's going to be 4.5 feet. As t is 3 seconds, the distance is going to be, so 3 squared is 9, plus 3.5 is 12.5 feet. And they want to know the change in the distance. So the change in d would be positive 8, right? We go from 4.5 to 12.5, and that's an increase of 8 feet. Okay, so it says on part B, draw a graph that illustrates d in terms of t, then illustrate each of the following on the graph. If we're going to graph, we have to consider how we would label that graph. That's very important. And so let's start there. Let's start by labeling the horizontal and vertical axes. Well, it says that it's the distance d, t seconds since the car started moving. So that's really another way of saying d in terms of t, which they give us here in part B. In terms of t, labels t as, the time in seconds since the car started moving. And then likewise, our horizontal then would be d, the distance in feet from that stop sign, or from that crosswalk, excuse me. Let's turn that over. All right. No, that's not what I meant to do. Sorry. Here we go. Let's put that right here. Okay. So they want us to graph. So they want to graph the increase in t from 1 to 3 seconds. So we've done some of that stuff already. We've done a little bit of work that way. So let's just go ahead and do that. Oh, actually, the other thing we need to do is we need to figure out how to label the axes. And it doesn't look like we're going very far in terms of seconds. And these boxes are really small. So I think I'm going to use like 3 boxes for 1. Not that way, though. Geez. So I'm going to use 3 boxes for 1. So we've got 1, 2, 3. 1, 2, 3. 1, 2, 3. So this would each be 1 second. And then for feet, well, we've already gone from like 4.5 to 12.5. So maybe we just do every 2 boxes here. So this is 1, 2, 3, 4, 5, 6, 7, 8. Oh, it looks like those are going pretty fast. 9, 10. So we would only get about 20 feet total. So let's make each of these 2, right? So each box is actually going to represent 1. So if we go from 1 to green, if we go from 1 to 3 seconds, then we're going to go from here over to here. It's a terrible, terrible line. Let's try that again. Well, okay, here we go. So from 1 to 3 seconds, that's a little bit better. So we've got a change in t of 3. Okay, and then it says the corresponding change in the distance from the crosswalk as the value of t increased from 1 to 3 seconds. So now we have to go, okay, so we started, so we've got 1 to 3 here. The distance changed from 4.5 to 12.5. So we go to 4 and, oopsie, we go 4.5 to 12.5. So we'd have, oh, stop that. We'd go from 4.5 to 12.5. So that's going to be 4, 6, 8, 10, 12.5 would be here-ish, right? So we'd go from here to here. And that would give us a change in D of 8, right? Okay. So, and if we wanted to label that, oh goodness, I keep hitting the side of the screen. Sorry, guys. If we wanted to go 1, 4.5 to 3, 12.5. Oh goodness, this is hard to do with vertigo. Anyway, we would have this right here, and our changes would look, goodness. Our changes would look like this. So we would have, oh goodness. Oh, good grief. Let's go this way. You guys would laugh if you could see me. I've got my computer upside down so that I'm not touching the side of it. And it's looking pretty silly. Oh, I did miss that one, didn't I? It should be here. Goodness, vertigo is really killing me. All right, so now here's a question. Part C. True or false, the car travels at a constant speed as the value of t increases from 1 to 3 seconds. Now, true or false, it is easier to disprove something in math than it is to prove it. And so, so your challenge here is to think about, if you don't think it's true, how could you disprove it? If you do think it's true, how could you prove it? And the first is definitely easier than the second. In this particular case, and take a second to pause, think about that. In this case, it is easy to show that it is false. A really simple proof would be to say, think about where we are at the second. So if we say that the distance is 2 squared plus 3.5, then we would have 4 plus 3.5, which is 7.5. Well, check out where that falls here on the graph. My terrible, terrible graph. Here we go. So we've got, goodness. Oh my goodness. This is not drawn very well, is it? Because here's 3 right here. Gosh, Melody. Okay. Let's try to fix this. Sorry, guys. That's some terrible drawing I did. Let's try that again. So there it is. So if we did 2, gosh, if we did 2, 7.5, we'd go 2, and we'd have, let's see, this is 2, this is 4, 6, 7.5, right? And we connected these two with a straight line. It just misses it, right? So there's this curving that needs to happen to make that happen. And my graph is not beautiful, but there's a definite curving that happens. In fact, we can go over to Desmos and prove that to ourselves. Let's go to Desmos real quick. There it is. And let's just graph D equals t squared plus 3.5. Now, because I'm using an electronic graphing calculator, it's going to be necessary that I change this into the language that Desmos speaks. So I'm going to use X and Y instead of T and D. But if we look at this 3.5, right? In fact, let's zoom in on that. Whoopsie. Let's zoom in on that. And you can actually see, follow me along here. So I've got 0, 3.5. Let me follow it with my stylus here. We've got 0, 3.5. And we've got, here we go, we've got 1, 4.5, and 2, where is he? 2, 7.5, right? Right in there. And if we kept going, we'd have to actually move up a little bit. We get to the 12.5 that was up there, right? So the 312.5. So you can see the curve in it. So if we actually just drew those 2 points that we found before, the 1, 4.5, and the 3, 12.5, and and we were to draw a line in between those, well, then we would end up with a very different, we'd have this straight line going between them instead of the curved line. And it's if we zoomed out a little bit, it might be easier to see that. See here, there we go. If we zoom kind of sideways, then that's a little bit easier to see. But this straight line doesn't fit here. So looking at this idea of rate of change, instead of calling this 8 the constant rate of change, this 8 here becomes the average. Whoops. Helps us to find the average rate of change. Sorry. Is that on the next slide? I can't remember. I'm not going to worry about that right now. Here we go. So we're going to call that the average rate of change. In fact, let's just put in a new slide because my brain is really starting to make way for the vertigo here. So this point here, I'm going to try something. I hope this doesn't kill my recording. Let's see what happens. Anyway, let's see if I'm still recording in a minute. Oh, hope so. So the change in x of 2 seconds, right, from 1 to 3, and the change in y of 8 feet from 4.5 to 12.5 can be used to find the average rate of change. Sometimes mathematicians will denote that as the m, but with a line over the top of it, which means the mean or the average. I'm not going to do that here because I don't think the book uses that notation, but if you've seen that in the past, this connects to that. So that means change in y over change in x, or actually, goodness, Melody, in this case, actually, not change in x and change in y, is it? No. It's the change in d over the change in t. So we had change in t here, and change in d here. So change in d over the change in t is going to be 8 over 4, or not 8 over 4. Gosh, Melody, you need to stop. Sorry. 8 over 2, or 4 feet per second average speed from 1 second to 3 seconds. And I think that's where I'm going to stop things today. We'll have some more things to talk about tomorrow. Again, you are welcome to come to my office hours if you don't have class tomorrow. If you'd like to actually join either my 10:20 or 11:30 class tomorrow, we can make some room for you. The groups will be weird, but we'll make it work. I don't want you to miss out on class if you're worried about that. Anyway, hopefully you will have. You're keeping up with your Module 2 homework. I know the Module 1 homework has been just cumbersome thus far, and I appreciate you keeping up with that. I did extend the Module 1 Assignment 3 to tonight, so that if you haven't turned it in already, you can do that for tonight and not be late. And then, so we'll go from there. So anyway, so that is the end of this video. I hope that you are finding it helpful. I have to go surrender to my migraine now, and I will see you hopefully in class or in my office tomorrow or Monday, getting ready for that test on Tuesday and Wednesday. So thanks so much for your attention. I hope this has been useful, and happy studying.